Section 5 from Chapter 10 on the Binomial Theorem. So binomial expansion, if you have a binomial raised to a power, we are used to anything, of course, being raised to the 0 power equals itself, being raised to the first power, and then squaring something, we know we either FOIL or box the binomial together. And then if you have any other power higher than that, you would just FOIL or multiply those binomials until you've expanded it all out. So listed here is the binomial expansion from the 0 power to the 5th power. And I want you to look at those terms as you're writing them and see if you notice any patterns. And on the next slide, I'm going to talk about those patterns that exist and how we can use those patterns to expand a binomial without actually multiplying it all out, because that could get very tedious, especially if you have it raised to the 15th power or to the 100th power. You don't want to do all that work to multiply all those binomials. So write these expansions down, and then we're going to talk about what patterns occur in this binomial expansion. So you notice that each expansion has n plus 1 terms. So whatever that highest exponent is, then you're going to have one more than that terms in the sequence. The first term is a to the nth power, and the last term is b to the nth power. In successive terms, the powers of a decrease by 1, and the powers of b increase by 1. So you notice that the exponents are alternating. While a is increasing in exponent or decreasing in exponent, b is doing the opposite. It's increasing. The sum of the exponents in each term is n, so the sum of those exponents should always be added together to equal that n power. The coefficients increase and then decrease in a symmetric pattern. So you should see that the leading coefficient of each term, they go up and then they go back down. And we're going to look at the patterns that occur within those coefficients next. So the binomial coefficients can be arranged in a triangular array, and we call it Pascal's Triangle. So if the row number on the left-hand side tells you what that highest exponent is, 0, exponent 1, 2, etc. And these are just the coefficients, the numbers that go out in front of each term. So if you look at this array of numbers, you can see some patterns here as well. So we want to continue that pattern for the 6th and 7th row. We could continue on infinitely as far as we need, but we're just going to go to the 7th row for right now. So if you notice, there is a pattern when you go from one row to the next on what those numbers are. So we're going to fill in the 6th row. The first and the last number are always going to be 1. To get the next number in the sequence, you're going to add the two numbers from above. So 1 plus 5 is 6. The next number, I would add 5 and 10 to get 15. 10 plus 10 is 20. And then the numbers are going to decrease in the same order. So 5 plus 10, again, is 15. 5 plus 1 is 6. And then don't forget your 1 at the very end. So if you look at any of the rows above, then to get that specific number that you're looking at, all you have to do is add the two numbers above it that would form a triangle. So for the 7th row, again, we're going to start with 1. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. And then we're going to continue. That's going to be 35 again, 21, 7, and 1. So we could keep going on Pascal's triangle, and whatever that highest exponent is that we're trying to raise that binomial to, these are the coefficients for that binomial. So we can use Pascal's triangle and some of the patterns that exist within the exponents to fill in and find a binomial expansion without actually having to multiply it all out. So in example 1, it wants us to use Pascal's triangle to expand the binomial x plus y to the 7th power. So without Pascal's triangle and noticing these patterns, we would have to multiply x plus y times itself 7 times. So that would get pretty tedious and pretty messy as you go. Instead, I'm going to go ahead and list out those coefficients from the 7th row of Pascal's triangle. We're going to need these coefficients, and then we're going to be following some patterns that exist within the exponents. You also need to identify what a and b are in this binomial, and we will use those to follow some patterns. So our a in this binomial is x, and our b is y. So we're going to start with the leading coefficient for the first term. That's going to be 1. Your a term will always be raised to that highest power to start with, and your b term will be raised to the 0 power. Okay, I'm going to come back and simplify all these terms at the very end, but first we're just going to fill them in. So the second term is going to start with 7, x to the 6th power, and y to the 1st power. Okay, your a term is going to decrease in power as we go, and your b term is going to increase in power. The next term will be plus 21, x to the 5th, y squared. We're going to continue this pattern. So plus 35, x to the 4th, y to the 3rd. Plus 35, x cubed, y to the 4th. Plus 21, x squared, y to the 5th. Plus 7, x to the 1st, y to the 6th. And then last, plus 1, x to the 0, y to the 7th. So in the first step, I would go ahead and write it all out exactly like this. Put your coefficient out front, put your a and b, and then write the correct exponent. For this binomial, it's fairly easy since the terms are just x and y that we're raising to a power. So it's going to be simple to simplify each of these terms and then to write the full expansion out. Once you start adding in another coefficient with your a or an exponent, that's when it gets a little more complicated. So I'm going to write my final answer out. So this is going to be x to the 7th plus 7x to the 6th y plus 21x to the 5th y squared plus 35x to the 4th y cubed plus 35x to the 3rd y to the 4th plus 21x squared y to the 5th plus 7xy to the 6th and plus y to the 7th. So if I multiplied x plus y times itself 7 times and wrote all that out, in the end, this would be my binomial expansion. Okay, we're going to do another example using Pascal's triangle. This time we're raising to the 3rd power, so I'm going to write down the numbers for the 3rd row. So this will be 1, 3, 3, 1. So we need to identify our a and b. This time a is equal to 2x and b is equal to negative 7. So you need your coefficient, which is going to be 1 times your a to the highest power and b to the 0 power to start. So 1 times 2x cubed times negative 7 to the 0. Plus 3 times 2x squared times negative 7 to the 1st. Plus 3 times 2x to the 1st times negative 7 squared. And then plus 1 times 2x to the 0 times negative 7 to the 3rd. So the first time, like I said before, I would write it all out, keep your coefficients, keep your exponents so you can see those patterns that exist. Then you can come back and simplify each term. So we need to do 2 to the 3rd power times 1, and we know that negative 7 to the 0 power is going to be 1. So that very first term is going to be 8x to the 3rd power. The second term, we would have 3 times 2 squared times negative 7 to the 1st, and that would be minus 84x squared. The next term would be 3 times 2 to the 1st times negative 7 squared, which will be plus 294x. And then the last term, 1 times 2 to the 0 times negative 7 cubed. It's going to be minus 343. This one wouldn't be too terrible to multiply 2x minus 7 times itself 3 times. You would FOIL the first pair of binomials, whatever you get, then multiply that times the third one. But if you did that, all that work, it would simplify to this polynomial. Okay, the formula for binomial coefficients of a plus b to the n power. So sometimes they want to know just one specific term within an expansion instead of multiplying the whole thing out, if you can find the value of this one term. So the coefficient of the a to the n minus r term times b to the r term of the expansion of a plus b to the n is given by the combination of n items choosing r items. You can use this formula n factorial over n minus r factorial times r factorial. So remember that the factorial is when you multiply that number times the subsequent numbers that come after it. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so you can use the formula if you want to, but our calculators actually have the combination feature underneath the probability, and we can do n choose r items in the calculator, and it makes life a little easier for us. So in your calculator, if you will go to the math button and then over to the probability menu, the third one down should be n choose r. And when you type this in your calculator, you have to have that n value first typed in, then do n choose r, then type the next value for r. The 84 pluses probably is easier to plug in those numbers. It'll probably let you plug them in like a little box. But the older 83 plus, you have to type the number, then n choose r, then the number. So n is that highest exponent in your binomial expansion, and then r is going to equal the term that you're finding minus 1. So in example 3, they want us to find the fifth term in the expansion of a minus b to the 13th power. So instead of us actually expanding a minus b to the 13th and then going over to the fifth term, we can use this formula to find the coefficient of that term and then use the rules with the exponents to find out what that whole term would be. So first off, our n is going to be 13, and then r is always the term minus 1, so in this case will be 4. So our a is a and our b is negative b in this case. So in my calculator, I'm going to do 13 choose 4 to find out what that coefficient value is going to be. So 13 choose 4. Then we're going to have to do a to the 13 minus 4 power times negative b to the 4th power. So 13 choose 4 turns out to be 715. And then a to the 9th times b to the 4th. If the a and b values were a number, obviously when you raise them to the power, then that number times the 715 out front would change that coefficient value. So if I was to fully expand a minus b to the 13th and I counted over to the fifth term, it would be 715, a to the 9th, b to the 4th. Okay, example 4 wants us to find the third term in the expansion of 2x minus 3y to the 8th power. So our n is going to be 8, since that's our exponent. R is going to be the term minus 1, so in this case it will be 2. Our a is 2x and b is negative 3y. So for the third term, we're going to do 8 choose 2 times 2x to the 8 minus 2 power times negative 3y to the second power. So in your calculator, when you do 8 choose 2, you get 28. And then we're going to have 2x raised to the 6th power. So I went ahead and did 2 to the 6th power, and that equals 64, x to the 6th. Then you have negative 3y squared. So negative 3 squared is going to be 9y squared. So now I'll just go ahead and multiply all those numbers out front. 28 times 64 times 9. And that equals 16,128 x to the 6th y squared. Okay, so you just have to make sure that you have your n and r values, and then in your calculator, do that number, choose 2, or choose how many ever, what term you're finding, minus 1. If you don't want to use that option, you can always go back to the formula at the very beginning and plug it into the formula.